Okay, so this is more or less the surprise chapter. I mean, it's just a very small intermediate chapter for you to see how we can extend the ideas of eigenvalues that you studied with Mr. Bynes to the general concept of a linear map. All right, and this is a very important notion, and there are plenty of applications related to this. All right, so it's very important. All right, so this is just a summing up, more or less, because I think you have seen most of that. All right, so endomorphism reduction. That's a very nice word, isn't it? It's just a word that stands for diagonalization. When we are working in finite dimensional space, it means endomorphism. You understand now what it means. Endomorphism, it's just a linear map that goes from a space E to itself, right? So we're going to assume we've got a vector space E and we've got a map F that is a linear map from E to E. Okay, that's an endomorphism. And reduction, it's just that we are looking for specific properties of this endomorphism. We are looking for specific directions, if you remember what you did with eigenvalues. And if you remember, that would lead to diagonalization in finite dimension for matrices. And so you are reducing the number of important values to the proper values, to the eigenvalues. Okay, if you had a matrix full of coefficients, then if it is diagonalizable, you reduce you reduce the description of your matrix to only the values that come on the diagonal of a diagonal matrix. Okay, so that's what reduction comes from. All right, so so this is just a bit of a summing up of the important notions that you have to see. First, the eigenvalue. That's the first thing here. It's a definition. Okay, we have the definition. We have an eigenvalue. F has an eigenvalue. An eigenvalue doesn't come alone. It comes only with an eigenvector. Okay, so we have an eigenvalue if there exists a non-zero vector, which we're going to call the eigenvector, such that f applied to this vector is equal to lambda, this is this value, which is a real or complex value, times the vector. Okay, so you've already worked on that. Eigenvalue and eigenvector come together, right? You don't have any eigenvalue without any eigenvector, and you don't have any eigenvector without any eigenvalue, right? So they really come together. All right, so this definition, you must have already worked on that during semester 1 of this year. All right, so remember that. Maybe you haven't seen that word, the spectrum. Okay, spectrum. The spectrum. So that's another definition. The spectrum of a linear map of an endomorphism. So think always, when we say endomorphism, square matrix, right? That will be your basic representation. So think about a square matrix of size 3 times 3, for instance, or even 2 by 2. Okay, when we are talking about linear maps, you can think about the matrix in finite dimension. Endomorphism, you can think about a square matrix. Maybe I should have said that first. Right. So the spectrum of an endomorphism is just the set of all eigenvalues, right? So sometimes we write it as SP, spectrum of F is the set of lambda eigenvalue of F. Okay, that's as simple as that. All right, and if you think about that, it's just like having the eigenvalues. You already know the story. If you can find enough eigenvalues, you you will be able to diagonalize the matrix, and so your matrix will be represented by just this single diagonal. So maybe the word spectrum, I haven't been able to find exactly where it comes from, but that's a nice way to remember it. You have a very thin, very spectral representation of your matrix in the end. All right. Okay, so next point here, it's more of a property, but it's a very direct property. We said that we have an eigenvector that is associated to lambda. It means that this eigenvector belongs to the kernel of f minus lambda times the identity. Okay, or think matrices, null space of your matrix minus lambda times the identity matrix. All right, it comes directly from the definition as V is an eigenvector associated to lambda. It means that Fv is equal to lambda times V. That I've just translated the fact that lambda was an eigenvalue and V an associated eigenvector. So that means that you can write it as Fv minus lambda V is equal to 0. Lambda V, you can write it as V lambda times identity of E times V. The same way you can write that the vector is the identity matrix times the vector. Okay, so F of V minus lambda identity of V is equal to 0. All these being linear maps, you can write that it's on even it's just maps. It's the map F minus lambda times identity map applied to V. So it's F minus lambda identity applied to V is equal to 0, which translates into the fact that V belongs to the kernel of F minus lambda identity of V. Okay, so that's why when you are looking for the eigenvector, one way to do that, one very common way to do that is to find all the elements that belong to the kernel of your map minus lambda once you have found the eigenvalue minus lambda times the identity. Okay. Next thing, that's again a definition, the eigenspace, right? It's, well, the eigenspace is going to be exactly that one, okay? That's what we usually, the name we give to that space is E with a subscript of the eigenvalue. Okay, it corresponds to the kernel of F minus lambda identity of E, and you know that it is a vector space because we have already proved that the kernel of a map, a linear map, okay, and in that case it's the linear map F minus lambda I, is itself a vector space. Okay, next thing, this one. Okay, that's an important thing.